Hi there everyone. Welcome to the video lecture series on Taylor series and Laurent series in complex analysis. So far we had been studying complex integration. Now let me tell you, complex analysis is a branch of mathematics. It's a entire big area of study under its own right. Under that comes the topic of complex integration. As we excel in the topic, as we advance, we encounter some more and more complex and difficult notions. So, for that, we need some concepts, and amongst that comes Taylor's and Laurent series. So, let us see how we can understand them. Now, if you have seen Taylor series in your lower classes or in any other semesters, it's fine. Now you will see the general form. So Laurent series rules over it. Okay, so Taylor series is a part of a Laurent series, you will see now. So let us see how all things are important. Now, first of all, if you have not ever encountered what is called a series, let me give you some important notions over here. So first of all, a series means something goes on a total of terms which goes on infinitely. Okay, if it is a finite number of total terms you are adding, it's not a series, it's a summand. Okay, but a summation where infinite number of terms are added together, it's going to be called as a series in mathematics. So there's a very important distinction between summation and a series. So when you take up a series of this format, z minus a to the power n, with some constants cn over here, where n is running from 1 to infinity, such a series is called a power series. Now this power series is in the powers of z minus a we will be getting, and these ci's are called the constant, z is the complex variable, and a is called the center of the series. Over here with power series, there are few notions are there, or I would say few concepts are attached. For time being, we can keep them aside. Okay, something like radius of convergence and whether the series is convergent or not, and etc. etc. We'll not discuss them at this stage. Right now, we'll focus upon the basic understanding. So this is what is called a power series in the very simple layman language. So this is the power series. Okay, this is the definition over here. Now let us go to some important expansions which are required for the topic. One of the most important expansion that we will need is 1 over 1 plus z. It is equal to 1 minus z plus z square minus z cube plus z raised to 4 minus so on. It goes where mod z is less than 1. This is very crucial. Okay, we need to remember this point over here. This condition is going to be very useful throughout Laurent series topic. Another thing over here is that, see, this form which we have uh, seen here, okay, this entire thing is called the expanded form of 1 upon 1 plus z. It is the expansion in terms or in the powers of z, right? So this is called the expanded form. There is one more form over here which I would like to mention. It is 1 upon 1 plus z. This expanded form, it is all the time in mathematics, you can't go on expanding. So there is something called as a compact form or a summation form. Let me show you how we can write it. It is just the style of writing it in a different way. Okay, so this can be written as summation minus of 1 to the power k, z to the power k. And here it is k running from 0 to infinity. Now why I have done this? Because I can see here every alternate term is having minus, plus, minus, plus. Moreover, I can see that there is minus term sign coming to every power of z, which is an odd power. Okay, so I have done this adjustment and have tried to write it compactly. Such a form is called summation for, okay, summation form, or it is also called as compact form. Sometimes it is called compact form. Sometimes it is also called as a closed form. Okay, it depends upon the teacher or the student or the author who is explaining the part. So this is the very important thing that we need to know: the summation and the or the compact form. Okay. Let us see the another expansion. This is again a very crucial and a very important expansion: 1 upon 1 minus z. Just replace in the above format z by minus z. We will get this expansion: 1 plus z square plus z cube plus z raised to 4. Again, this is very important. Its expansion has the following compact form. It is summation. It's very easy to remember: z to the power k, k running from 0 to infinity. This is very important. Now, there are few others also that are very important according to me. You may encounter these, but I'm not taking their compact form right now, because I right now do not feel they are too much important. But whichever are important, I'm giving you. So let me just highlight here. These are very important. We will need them throughout. So be very careful with these two formulas and remember them. Another important formula will be 1 upon 1 plus z square. You can just take the this formula and you replace z by minus z, you get that. Now all these four formulas have been derived from this important formula of log of 1 plus z. Okay, so if you understand this, it's very important. For as a mathematics student, you would really have this curiosity to, you know, how to handle these kind of expansion. I'll just give you a hint. Log of 1 plus z, if you can remember this expansion, you will have to take the derivative. If you take the derivative of log of 1 plus z, you get the following. The first result will be given to you. Then in the first result, you replace it by minus of z, the z to be replaced by minus z, you get the second result. Now in the second result, you in order to get the second result, take the derivative of this result over here. Uh, no, to get the third result, I mean to say, take the derivative on both the sides, you get the answer. So they all are interconnected, and yeah, so log of 1 plus z is the main expansion formula from which all the above four formulas have been derived. Okay, so we need not worry about log, but the two that have come, the 1 upon 1 plus z and 1 upon 1 minus z, these are very crucial to our expansion and understanding. As and when we will need them, we will use it. Okay, and also be acquainted with this summation format or compact form. The reason I am telling, because if you are studying engineering, or if you have somewhere transforms into your topic, then something called as z transform is very crucial and very in line with Laurent series. So this kind of summations are very often seen over there too. So that's why this compact form is very crucial. Now let us see how to handle other expansions. So some other expansions are e to the power z. Now this expansion can be also seen with a compact form. Let me give you the compact form. So is it is going to be one, the expansion here you see it is 1 plus z square over 2 factorial z cube over 3 factorial and so on, right? So e to the power z, its compact form is summation z to the power k over k factorial, where k runs from 0 to infinity. This is the expansion. Now with e to the power z, two most important trigonometric for expansions I am giving you, they are sin z and cos z. You just need to remember sin z thoroughly. You can remember cos z easily. You take the derivative of sin z, it's cos z. So take the derivative of the expansion on the RHS. So z derivative is 1, z cube derivative is 3z square, and 3 cancel, so 2 factorial, like that. So if you understand, it's just taking the derivative. The important expansion that we come across is sine h of z, the hyperbolic sine function. Now since sine h of z has come, again similarly we can take the derivative of sine h of z, we get cos h of z. So I'll just write over here to show you. So if you take the derivative over here on the sine h of z side, LHS, over here if you take the derivative you get cos h of z, and its expansion will be 1 plus z square over 2 factorial plus, here we will have z raised to 4 over 4 factorial plus z raised to 6 over 6 factorial plus, and so on. Okay, so this is how the expansion happens for cos h of z, and again the condition is same, mod z is less than infinity. So these are few expansions which are important. Of course there are others also we might need. We will see them when we need them. Okay, so let us go for another expansion formula for Taylor series. Now Taylor series formula is this over here. If f of z is analytic, when I say analytic, it means Cauchy-Riemann equation and all other fundamental theory of differentiability that we have understood in our previous classes that would be needed. So inside a circle, when you have the analytic function centered at z0, then for all the points inside the C, circle C, you have the following expansion. F of z can be written in this manner. Now you need not worry what all these things are happening, okay? No, don't get scared of all these expansions and the formula. You just have to understand them in a very systematic way. It's, see, I'll just expand it. It is f of z. When you expand it, what do you get? N equals to 0, you get over here it is f of 0 z evaluated at 0. Then when n it is 1, you just have z minus z naught to the power 1 over 1 factorial times the first derivative evaluated at z naught. Then there is z minus z naught whole raised to 2 over 2 factorial f double dash at z naught, and so on. Okay, so let's just write z minus z naught whole raised to 3 and 3 factorial f triple dash at z naught, and this goes on. So this expansion we have seen. Now you see that if you write this long mathematical expansion, it's very confusing for or it may be very tedious. That's why that compact version is given. So compact version, if you don't follow, take some time and expand, or if you like that expanded version, stick to that. Now in this formula, there is one easy formula sitting down. If you put z0 equals to 0, then the Taylor series become a Maclaurin series. Okay, that's the only thing that is new in this Maclaurin series. Otherwise, not a big difference. So you can remember the Taylor series formula. Now comes a very important part of complex analysis, that is Laurent series expansion. Now what I would say that to all my viewers, those who are watching this, you can write down this definition as I am giving you over here. You need not worry how and all these mathematical terms are, you know, going all around and what all things are happening. I'll explain you. You can take a screenshot of the whole thing, and we will understand it part by part. So it looks very tricky, it looks very difficult at the initial stage. Believe me, while solving, you need not bother about so many stuff. It is technical, precise mathematics. The reason why it is like this, see, in mathematics, everything needs to be very precise. Okay, so that's why we have all the technology, booming at the best because of these precise formulas. So that's why they are very precise and maybe a little bit tough or difficult at in their language, but they are beautiful. So let me just explain you the whole definition, and we can understand it in a easy way while solving the problem. Solving, believe me, is not this difficult at all. It's extremely easy. We just need to remember few expansions and we are done. Now see, here it says are two concentric circles. Okay, I'll just take a yellow pen over here. There are two concentric circles of radii 1 and 2. Either one is r1 is greater than r2 or something like that, and it is centered at z naught. Okay, so if you have this as a z naught, and I'll draw one circle. Okay, it's roughly a circle, and here one more circle. Okay, yeah, just something like that. So if you have one r1 here and another r2 over here, so in this is the annular region. The annular region, in that, all these things, this is working. Now let me explain you what the Laurent series definition basically means. See here, Laurent series is, I'll give you this general version here. If you have this function f of z, the summation, let's see, n z minus z naught to the power n. Okay, and this n is going from minus infinity to infinity. When you have it this way, now it is very difficult to understand minus infinity to infinity. So many terms are there. So you break up into two parts. So you break this up as two parts, Cn z going from z minus z naught, n running from minus infinity to, we'll take it up to minus 1. Okay, and here I take it up from z running n running from 0 to infinity, positive infinity, Cn z minus z naught to the power n. Now this same thing which I have written over here is written in this double star equation. Try to understand what is happening. Now that whole thing is just simplified a bit and written in a nice manner. Okay, because n is going from minus infinity, n is taking all negative values. They have written it, this whole thing, as summation Cn z minus z naught minus n. Now so I can now write n running from 1 to infinity. Now it will not bother. And here there is this Cn and z running from z naught to n going from 0 to infinity. I hope you get that. Now for each part, when the power of z minus z naught is negative, this Cn is having a special formula, and here when it is a positive power, z minus z naught power is positive, this Cn has a special formula. So this is called Bn and this is called An. That's the whole story. Okay, that's those two formulas I have mentioned over here. We are not going to use these formulas at all. Don't worry. This is technical mathematics. So I just explaining you how it is working. But yeah, we do need to know the name of the part. So this part, okay, the part which I'll just put it in a red color, this part where the powers of z minus z naught are negative. That means you will have, if you expand this a little bit more, summation Cn, this will be written as z naught whole raised to n. It will be in the denominator. So whenever you will have any term in the denominator, okay, z minus z naught to the power n, this whole function part or the expansion part is in the denominator. This part is entire part is called principal part. Okay, that is what I have mentioned here. It's called the principal part. And the other part where z minus z naught powers are positive, the powers are positive, it is called the analytic part. Now, this principal part that we just saw is the deciding factor whether we are going to have our answer as Taylor series or Laurent series. Okay, and this is where the advanced stories begin. So it is just all mathematical understanding about how the things are derived. Now, all the other advanced part which is related to the order of the poles, the types of singularities, and etc., we will not deal it over here. Okay, I'll just take up solving of the example now, because this much of theory is enough for us to understand what is what and how to fix up the things. So these two formulas I have like these two formulas which I marked over here, we are not going to use them either. Okay, maybe if you are from any kind of a coding background, you may need them. That's why I have given you like in order to code in your computer or something. But the solving part of mathematics is a way different story than this technical definition. Okay, I might sound funny, but yeah, believe me, it's very easy to solve Laurent series questions. They are not this difficult. How this definition looks. This definition helps us when the function is very complicated. That time these definitions prove to a great help. Now let us see some examples. So I have taken here for the given function f of z 1 upon z minus 1 z minus 2, find the Laurent series expansion over here. Now remember, we have to find Laurent series expansion. So the step number 1 over here. So first step I'll take up here with the blue pen. Okay, step number 1 is find the partial fraction. Find the partial fraction of f of z. Okay, um, yeah, I think I have put a this straight line is there so that I can, not jump over the other region. So yeah, so when we have this, this is the step number 1 we are supposed to do. So let us do this step number 1. So f of z is 1 over z minus 1 z minus 2. Now, how do we find the partial fraction? So partial fraction, consider 1 over z minus 1 z minus 2. Now be very very careful. I would always suggest all my students here, this alphabet z and the numerical 2, please make some distinguishing between them, because I see every year students make, they are in a great hurry and they write z minus 2. Now it, to the student it is appearing z minus 2, but if you see z minus z, it appears like that. So if you have your writing style a little bit not so good, I would suggest you please use this kind of 2 and z, or you can just cut your z in this way. Okay, so this is very crucial because later on you also do not remember what you have written. So all please write it very clearly for your teacher to evaluate your answer. So a over z minus 1 plus b over z minus 2. When we do this, what we are now supposed to do, multiply the denominator onto both the sides. We get a times z minus 2 plus b times z minus 1. This is the thing that we will get. Now, over here, what is important is we have to find a and b, right? So we put z equal to 1. So when I put z equal to 1, I obviously get here that is 1 is equals to minus of a, which implies that a is minus 1. Then again when I put z equals to 2, okay, I get 1 is equals to b, okay, I get now therefore b is 1. So therefore my function f of z can be written as minus of 1 over z minus 1 plus 1 over z minus 2. So this is very important. I'll put a red mark here, 1. This is the function that I am going to consider. Now comes the case number 1. So let us go for the case number 1. I'll use this green color, case 1. So the case 1 says that it is mod of z minus mod z is less than 1. What is the meaning of this? We have to understand this. See, our denominator becomes 0 at two places, that is z equal to 1 and z equal to 2. Okay, in the partial fraction we can see, as well as in the function also we can see. So now those 2 points that are there, we can see them where the denominator becomes 0. Those are 1 and 2. So consider those points. So here it also means that mod z, since it is less than 1, it is less than 2. So it means here that it is mod z is less than 2. Fine. Now remember, we have to make everything less than 1. Everything should become less than 1. Then everything will settle down. And I'll tell you why everything has to become less than 1. Mod z is less than 2. So this can be now written as mod of z upon 2 is less than 1. This is very crucial. Now, in this partial fraction that we have taken, try to establish the factor of mod z less than mod z upon 2 less than 1. So let me show you how does it happen. This minus 1 over z minus 1 plus 1 over z minus 2. We have to make everything less than 1. You have to now remember the format that we had seen. The format of expansion was 1 upon 1 plus z, okay, which is same as 1 minus z plus z square minus z cube and so on, right? And another expansion format was 1 upon 1 minus z, that is 1 plus z square plus z cube and so on. So in this format we had the two important condition. The condition was mod of z is less than 1. This is the reason we are making everything less than 1, because we can write this expansion. And there are other technical reasons also. We'll not go into those detail, but this you can hold on right now. So try to bring your answer in this format, 1 upon 1 plus or 1 upon 1 minus. So I am now trying to write this as f of z equal to 1 upon, this minus sign can be written as 1 upon 1 minus z. This can be pushed down, okay? And then this 2 I can take and write down here as minus of 1 upon 2 minus z, okay? And what I'll do further, I'll take 2 common. So I get 1 upon 1 minus z, and when I take 2 common over here, I'll get 1 upon z by 2, okay? Now observe carefully. Yeah, I have established this mod of z by 2 less than 1 in my expansion or the partial fraction format. Can you see z by 2 has come here? Here. This was the important thing that we see here. Why did we do everything less than 1? The one reason, we have these two formulas for expansion. And once we do that, and we have to see the condition what it is given. Mod z less than 1. Now when mod z is less than 1, what happens to mod z less than 2? So mod z less than 2, we can write it as mod of z upon 2 less than 1. Therefore, now we are in a position to write the expansion of both of the terms. Okay, so let us see how to expand them. This expansion can be written as 1 plus z plus z square plus z cube plus and so on. This can go on. Now there is minus. This 1 by 2 will remain as it is. Now instead of z, I have z upon 2. So just change in the formula over here. I can write it in this formula. You change z with z by 2. So here you will have 1 plus z by 2 plus z by 2 the whole square plus z by 2 the whole cube plus and so on. It just goes on expanding. So you have now got your answer for the expansion. 1 plus z square plus z cube. This can be written as it is. Okay, no change over here. Now this here is nothing but minus of half. Then there is minus of z by 2 square. Okay, then here there is minus of z square over 2 cube. Then there is minus of z raised to 3 over 2 raised to 4 plus and so on. So when I do the following substitutions, collect the like powers, I'll get over here 1 minus 1 minus half I will get as half. Then z minus z upon 2 square. So that will be, I'll just write here 1 minus 1 upon 4 times z plus, now there is z square and here there is z 1 upon 2 cube, right? So here I'll get 1 minus 1 upon 8. Then I have here z square. Then I have 1 minus 1 upon 2 raised to 4 z raised to 3 plus and so on. This is how it goes. So how we now little bit simplify it a bit more because we need nice numbers over here with a good coefficient. So here it will be 3 over 4 z, here it will be 7 over 8 z square, here it is 2 raised to 4. So it is 16, so here it would be 15 by 16 z cube, and so on. This goes on and on and on. Now, this is the answer for case 1. This answer, and now if we understand, we see only positive powers. There are no negative powers over here. Okay, because z is having positive power, z raised to 1, z raised to 2, z raised to 3. No negative power of z. So we do not have any principal part over here. It is all analytic part. So since we have only positive powers, this thing is called Taylor series. Okay, Taylor series expansion we have got. So this is Taylor series, but a Laurent series itself, because Taylor series is a smaller version of Laurent series, you can call it. Okay, so this is what expansion we get in this case. Now, what I would like to add over here is one very important thing, a little bit sophistication to the answer. We can keep this answer over here as we have kept, and I'll just explain you another way of writing the whole answer. I'll take up the whole step further. F of z equals to, it was here, 1 over, yeah, this was the expansion. F of z is 1 over z minus 1. Oh no, it was 1 minus z, 1 minus z minus of 1 by 2, 1 minus z over 2. Right? This was the expansion that we obtained. Now we can do a little bit manipulation over here. We did write the whole thing by expanding, and we saw that there was a lot of numbers coming into the picture. To avoid all that, we can use the compact form of the expansion. Now we have already claimed that mod z is less than 1, and we have also said that mod z by 2 is less than 1. Because of this two important conditions that we have understood from the case 1, our answer now is in a position to be written in a compact form. So that compact form, that will be summation. The compact form for 1 minus z was z raised to k going from 0 to infinity. Done. Then here there is minus of 1 by 2, and this could be written easily as z to the power, instead of k, instead of z, we will now add z by 2 whole to the power k, right? K going from 0 to infinity. This is what we will have. Now simplify this. Summation z raised to k minus, now this minus, you keep it as it is and take this 1 by 2 inside the summation sign, because it is a constant, you can take it there, and here you can write this z raised to k over 2 to the power k plus 1, where k goes from 0 to infinity. I can now see here runner is starting from 0 to infinity, here also 0 to infinity. I can take the summation sign common. So I can now write summation k going from 0 to infinity. And this z to the power k can be taken common outside over here. So I'll write z raised to k. Inside it will be 1 minus 1 upon 2 to the power k plus 1. So this expansion we are done, and here now we are in a position to write any term in the expansion of the series. This is the beauty of compact form. You do not have to solve all the terms and everything. That same answer is now written in a precise manner over here. Now let me take up case number 2 and understand what happens there. So I'll write the answer here for case 2. Case 2 we have 1 is less than mod z less than 2. So there are two meanings over here. The first meaning is 1 is less than mod z and mod z is less than 2. So the first meaning from here you have 1 upon mod z is less than 1 and mod of z by 2 is less than 1. These are the two meanings. Now remember, to convert everything should become less than 1. Okay, everything becomes less than 1. So let us do this. So our partial fraction that we had found was f of z is equals to minus of 1 over z minus 1 and it was plus of 1 upon z minus 2. So these were the things that we had obtained, right? So now we have to get from the partial fraction, somehow I have to establish the term that I have found over here. Without the modulus sign, I have to establish it inside the partial fraction. So how to get it done? So let us simplify it first. So f of z can be now written as 1 over 1 minus z. And then again over here I can see that the same thing happened. Minus of 1 by 2 can be taken common and I can write it as 1 minus z by 2. What we have to do is we have to establish this portion over here. Okay, so in this part how can I get that? It is here, and 1 upon mod z, which is here, that you see 1 upon mod z. So without modulus it will look like 1 upon z. So that I have to establish over the first portion. Okay, in the first one. That is how I have to establish it. So how can I do that? Now let us see. Here I'll do f of z. I'll write here as, I'll take from here z common. So when I take z common, I have 1 upon z minus 1. That is established. I have got 1 upon z. That was my goal, right? We got it. And here I have a minus of half outside, and here the whole thing is 1 upon 1 minus z by 2. We are done with this. Now, but here there is some format missing, because our format for expansion is 1 upon 1 minus z format, or we can establish as 1 upon 1 plus z, right? 1 upon 1 plus z. These are the two formulas that I told you to remember. So now in this case I will write it as f of z equal to minus of 1 by z times 1 minus 1 upon z, and here it is minus of 1 by 2 times 1 upon 1 minus z by 2. These are done. Now we go for the expansion. So instead of expanding, we'll write the compact form. Let us try to write the compact form. So what was the compact form for 1 upon 1 minus z? The compact form was z summation z raised to k, k running from 0 to infinity. Okay. Instead of now for z, I have 1 upon z over here. Can you see this 1 upon z? Therefore, minus of 1 by z. And now this will become summation. Instead of z, I will have 1 upon z whole raised to k. K running from 0 to infinity. And minus of 1 by 2. And here the whole thing same. Summation. Instead of z, I have z by 2. So I will write now z upon 2 whole to the power k. K going from 0 to infinity. Now simplify a bit further. I'll get minus sign as it is. 1 upon z to the power k plus 1. K going from 0 to infinity. Okay. Minus 1. Yeah, that minus sign, we'll keep it outside, and we will have here minus of summation z raised to k upon 2 raised to k plus 1, k going from 0 to infinity. Now there is no scope of simplification. You can't take summation common and everything. Then don't do that. We have to now understand what does this say. Okay, this is the Laurent series. Okay, for case number 2 we have got our answer. If you leave your answer over here, it is absolutely fine and it is absolutely correct. Okay, no teacher will deduct your marks, but we have to understand what does it say. So if we expand it, if we want to expand, okay, just let us see what happens when we expand it. I'll just put it in this yellow box over here. Now I'll just expand over here with some different color. I'm writing f of z. This minus sign remains outside, and then I have all the powers coming here. So it is 1 over z plus 1 over z square, then 1 over z cube, and then 1 over z raised to 4, like that, and plus so on. They go on over here. Now in the minus part, the other part over here, we have k going from 0, right? So when you put 0 over here, you will have 1 upon 2, then you will have z over 2 square, then here you will have z cube over 2 raised to 3, no, not 2 raised to 3, just a minute, here you will have, yeah, here you will have z square, and then there will be z raised to 3 over 2 raised to 4, and like that. So this expansion we got. Now what is very very important in this expansion to understand is that we have one analytical part and one the principal part. The principal part is where you see the z is in the denominator. So it is this part, z is in the denominator, and it is here the z powers are positive. So this is the Laurent series that we have. Now let us go for case number 3. For case number 3, again we will consider this. Let us take down the case 3. Case 3. For case 3, let us see what happens. It is 2 is less than mod z. That is the case given to us. So what is the meaning of this case? It means, again, I can now write 1 is less than 2 and it is less than mod z. So there are two meanings over here. The first meaning is 1 is obviously less than mod z, and another meaning is 2 is less than mod z. This means that, now remember, we have to make everything less than 1. So while making everything less than 1, it is 1 over mod z is less than 1, and 2 over mod z is less than 1. So we have got this. Now in our partial fraction that we derived, okay, the partial fraction that we had derived was f of z, which is minus of 1 over z minus 1 plus 1 over z minus 2. This was the partial fraction we had derived. At any cost, now my job becomes that I have to establish 1 upon z over here and 2 upon z here. So I have to try to get that so that I can expand it. Otherwise, there is no way to expand. So let us see how to do. And remember, you have to expand 1 over z. You have to bring in this term and 2 upon z over here. Now, how do we come to know that these terms are to be settled over here? This you have to understand. See, where is the singularity, or where does the denominator become 0? Denominator, like we have chosen radius as 1 right now. So 1 is here. In the denominator it is here. And here you have chosen 2 as the radius, and 2 in the denominator is over here. So you go to that part of your partial fraction. Okay. So now let us arrange the terms. So I'll take over here, I'll write it 1 minus z. Okay. And over here I will write it as the same way, the way it is. I want z 1 upon z in the partial fraction. So what I can do, I'll take z common. The moment I take z common, I will have 1 upon z minus 1 plus 1 upon z taken common, I will have 1 minus 2 upon z. Okay. Now remember the format of the expansion for the two functions that we had seen as a very important function was 1 upon 1 minus z, or it was 1 upon 1 plus z. So try to write them in that format. So that format I can get here when I say f of z can be written as 1 upon z into 1 minus 1 upon z. That is one way. Another way I can, here it is already settled down. Oh, when I write this, when I swap this term, minus sign will be taken common. Okay, so yeah, so over here I get this. We have got what we wanted. Now let us write down. So 1 upon f of z can be written down as minus of 1 upon z. Now the expansion of 1 upon 1 minus 1 upon 1 minus, the expansion was summation z to the power k, right? K going from 0 to infinity. Now instead of z, I have 1 upon z. So I will now write summation 1 upon z whole raised to k, k going from 0 to infinity. Just replace z by 1 upon z in the main formula that we have remembered. Then 1 upon z over here. Now instead of z, what do we have to write? 2 upon z. So here it is summation 2 upon z whole to the power k, k going from 0 to infinity. We are done, almost done, nothing more remaining. Start uh, simplifying the terms. I can put this minus outside, I can keep it here, and I can take z inside. I'll get z whole raised to k plus 1 over here, k going from 0 to infinity, and here what do I get? Summation 2 raised to k over z or k plus 1, k going from 0 to infinity. Done. So let us see what all terms come into the picture. I can now take summation sign common, and here I will keep z, I can keep this here, minus 1 here, and minus here I have 2 to the power k. Okay, so this is the answer for my expansion of the Laurent series. So this is the final answer in case 3. Just remember all the 3 cases. It was a pretty lengthy problem along with the theory that we saw. What I want you to go through all the 3 cases is this. Let me go to the first case. Yeah, this was a case 1. Step number 1 is that we have to find the partial fraction. Okay, once you find the partial fraction, go for the case which are given to you. In each case, try to see whether you have the uh, number which is there in the denominator. Can you get that? So I had 1 and 2 over here. So mod z is less than 1, therefore it is less than 2 also. Then you try to understand that case and try to bring everything less than 1. Okay, if even you have mod z less than 2, see I brought it less than 1. Okay, I made it less than 1. Now whatever terms that you create in this case while understanding it, that term you have to establish into your partial fraction. That is the place you have to bring it into the partial fraction. Once you bring that into the partial fraction, you are expected to write it in this formula format. These format you have to write 1 upon 1 plus z or 1 upon 1 minus z format. That was the key reason in that condition mod z is less than 1. That's why we were making everything less than 1. Then you expand it. Okay, on expansion, if you feel you want to write all these long terms, you can write the long terms, it's okay, it is still correct. Or you write the compact version which I showed you here. I prefer the compact one. Okay. Case 2, again see there how do you get the terms and then establish the terms in the partial fraction and then expand. Be very careful while expanding, do not do haphazardly, otherwise you'll land up into trouble. Go slowly and understand and do it. Case 3, again the same way, take your partial fraction and settle the term which comes along with the case. Each time from the case there will be 2 meanings. Okay, from each case that is given to you there will be 2 meanings, and from each of the meaning you will get a term. you will get some term, and that term you have to establish in the partial fraction and expand for the Laurent series. For now, this much is enough for our understanding. Please go through the entire example again. If you feel any difficulty, please uh, feel free to ask me in the comment section, okay? Or you can put your doubt in the comment section and let me know. I'll again take up some another examples. And remember, Laurent series examples are slightly lengthy in nature. Once you get the crux of the whole sum or the question, it's very easy. You just have to expand and write the summation quickly. Take the partial fraction, write the summation. Take the partial fraction, write the summation. Okay, so you don't have to worry about all the things. Once you understand the cases, it's done. So uh, I hope you have followed this long example along with the theory and everything. I have tried to take up the most easiest and the minimal part that was required for Laurent series, but this is the crucial kind of example that is asked in most of the examination for the students. So I have dealt with it over here. I hope you have liked the example. Please hit like button and share it with your friends, those who find it useful. And please subscribe to my channel. I'll see you with other examples in the other video lecture. Till then, keep solving good amount of mathematics. It's Mayur Gohil signing off. Thank you for joining.